system, which is the piston full of ideal gas, and how we can visualize the changes in different thermodynamic processes using PV diagrams. We also talked about energy transfer of using heat and work and conservation of energy through the first law of thermodynamics. And then we talked about a variety of different processes that are, in a sense, idealized, including isothermal, where the temperature doesn't change, isobaric, where the pressure doesn't change, isochoric, where the volume doesn't change, adiabatic, where no heat is added. We actually didn't talk about free expansion. We're going to talk about that today. We're going to first focus in this first part of the lecture on material properties, in particular speaking a little bit more about specific heat and some thermal expansion. So if we look at two different materials, aluminum and styrofoam, they have different specific heats, which you can find online. And if both of these change by the same temperature, then there's different amounts of heat that are transferred to them. And in particular, the aluminum transfers in 4,500 joules for a delta T of 50 Kelvin, whereas the styrofoam only transfers in 600 joules. And this heat capacity is, in a sense, it's the ability for this material to take in energy through heat exchange processes. And this ability to do this is actually based on the molecular interactions of the molecules within the system, and we'll talk about that in a second. We also learned last time that the heat capacity depends on the process of the heating. So for instance, if we have two different systems, one is an isobaric where the pressure is constant, we saw that its heat capacity was 5/2 nR, which is for an ideal gas. Whereas if you moved the same ideal gas through the same temperature shift, but you did it isochorically, so no volume was changed, then it's 3/2 nR. And you can see, just do the calculation straight out and see that it's true that the isobaric constant pressure has 1,000 joules, whereas the isochoric has 600 joules. This seems a little odd until you realize that what's happening is that when you have an isochoric, you can do no work. But when you have an isobaric, you can. And that means that for the constant pressure, even though it's held at constant pressure, because the volume can change, you actually can get some of the heat turns into work. And that means that you're not really able to turn, it's not all of the heat going into the system. Some of it's actually being lost due to work in the isobaric process. And that's why these heat capacities are different. So again, if we look a little bit closer at the molecules of the aluminum and the styrofoam, we can get an idea as to why you have different heat capacities. So the aluminum has aluminum atoms that are arranged in a lattice, whereas styrofoam has styrofoam polymers. In this case, they're kind of plastic polymers of a sort that are entangled and enmeshed with one another. The aluminum molecules have more space to vibrate around, whereas the styrofoam molecules cannot, and they can't move very easily. And so that vibration within the material allows more heat to be stored, because as you heat the system, each of these atoms is actually going to vibrate more. And certainly when aluminum is melted, it actually will, these molecules will vibrate so much that they will no longer be in a lattice and they'll be in a fluid instead. And so in a sense, we can think of this, when you transfer heat in, the material is storing it locally. It can be kinetic or potential energy, but it's storing it within the material. And so the heat is increasing the energy of the material, even in a solid, even when it's not an ideal gas. There's another thermal property of most solids, which is thermal expansion. And that's because as the molecules vibrate, they also take up more space. And that causes the material to expand upon heating. So thermal expansion is defined as the process of a material getting larger due to thermal heating of that material. And you've seen this before, because if you've ever had like a pickle jar that you couldn't get the lid off, you may know that heating it under warm water will actually allow the lid to expand and then loosen. And any place where you have two different materials coming into contact, you can actually get expansion of those materials through thermal expansion. And this is what causes, for instance, roads and things like this to deteriorate in the summertime when they expand, and then they contract in the winter, and then you get cracks in the roads. Now, one of the interesting things about one of our favorite substances, water, is that it's one of the only materials in the world that when it cools and freezes, it actually expands as well. That is very unusual. Most things, when they freeze, they actually become smaller. But because ice is actually slightly larger in its spacing of its molecules than water is, it actually allows the ice to float. And so this is one of the reasons why ice floats. And after this horrible, horrible winter that we had, this is also one of the reasons why you get potholes in the road. It's because the cracks that formed in the summertime, the water slips in and then it freezes, causing, and it expands, and it breaks up the asphalt as it expands. And then when the water contracts, or melts again, the water obviously contracts and then can slip away, but what you're left with is a big hole in the road. This is also the reason why your pipes will freeze and then crack when they're frozen. It's because the ice is expanding. So ice is the only common material that we use that actually expands upon cooling. Most materials will actually contract upon cooling and expand upon heating. So we can quantify this expansion using an easy equation, which says that the change in the length of a material, so this is for a linear material. So if we're looking at this aluminum block, let's just look at the length of the material on one side. That's equal to the coefficient of expansion, which we denote as alpha, times the original length of the material times the change in temperature. So as you increase this temperature, you'll actually see more expansion. If you increase the temperature too much, then you'll actually leave this linear regime of expansion, and you can get all kinds of other weird effects that are occurring, including melting. Another material property of different materials is thermal conductivity. So we talked earlier about having a hot block and a cold block, and they were in contact, thermal contact through a third block. That third block is a thermal conductor that can conduct the heat between the two, causing them to all come to equilibrium. And thermal conductivity is really important. We use it in a lot of different applications for heating and cooling. You can actually use this in order to actively cool systems, and having that it actually in contact with a thermal conductor that pulls heat away from the system. And this is actually interesting because it does depend on the vibrational modes of the atoms, but it also depends on the ability of the electrons to move in the material, because the electrons can actually conduct the thermal energy away, as well as the vibration modes of the atoms as they're sitting in their lattice. And so metals are particularly good thermal conductors as well as electrical conductors. And you're going to learn more about electrical conductivity in Physics 132 next semester.